In yesterday's lecture, we have discussed about aggregate size, shape and surface texture. Today, we are going to discuss about packing density, how we can combine aggregates in a different manner to reduce the porosity, etc. In last lecture, we have seen that aggregate as an inert material and it forms the skeleton of the concrete, and it constitutes about 60 to 75% of the volume. These and all we have discussed already. Here now what we are going to discuss is how this aggregate is being embedded in concrete in such a way that its packing reduces the volume of voids. This aggregates being larger in volume compared to others, this our main objective is to reduce the voids so that we can minimize the volume of cement paste which is going into the concrete, so that we can achieve economy. So, in order to do this, we have to achieve a good packing arrangement of aggregates. So we can reduce the voids. That is, for a normal concrete, we have to increase the aggregate content so that we can minimize the paste content. Why we should minimize the paste content is, since it's being costlier compared to the other materials, we are aiming for a lesser cement paste. That is, the interstitial space, that is nothing but voids in between the aggregates, will be occupied by the cement paste. So obviously if the voids between the aggregate is less, then a lesser volume of cement paste is okay. Then a lesser volume of cement paste will be enough to fill those spaces, interstitial void spaces. That is, the cement matrix will go in between these aggregates and enhances its that is, the cement paste will go in between these aggregates and ensures the dispersion of aggregates. So our main aim is to reduce the void content in an aggregate system so that a minimum paste content can be utilized. Next, coming the packing density. It is nothing but the volume of solids to the total volume. Volume of solids to the total volume, and this ratio, packing density, it's defined as a ratio between the volume of solids to the total volume, and it is given as 1 minus P, and this P is nothing but porosity. How the aggregates are being packed to ensure a minimum amount of void content or porosity. That should be the main aim. For that, let's see a small example. This porosity, how it changes when the aggregate are being packed in a different manner. Packing density of single sized aggregates. Now let's discuss about single sized aggregates alone. When these single sized aggregates are being packed together, how their packing density will be. Let's see through an example. For simple cubic packing, the relative porosity is around 48%. For simple cubic packing, the relative porosity is 48%. Let's see how that simple cubic packing will be. Assume this to be the aggregates when these aggregates are packed in a simple cubic manner, that is in all the three sides, assume it to be continued in this side, in all the three sides. A simple cubic packing. For this, the porosity is 48%. If the same single sized aggregates is being packed in a different manner, that is body centric, face centric, cubical manner, then the porosity percentage will vary depending upon the packing arrangement of particles. If the same particle is to be packed like this, then this will have a different porosity compared to this simple cubic packing system. Just the packing density of a single sized aggregate based on the simple cubic or body centric or face centric will vary from 0.5 to 0.68 and 0.74. This is nothing but packing density of single sized aggregate. The packing density of single sized aggregates based on its packing conditions like simple cubic or in a face centered cube or in a body centered cube, its density will vary from 0.52 to 0.74, and this is the reason why we used that 0.62% when to describe the size of the aggregate in the angularity number is based on this concept. That is somewhere it lies between 0.52 and 0.74. If it is a compactly packed aggregate, then its packing density will be around 0.74, and if it is a lessly compacted if it is a completely packed aggregate, then the packing density will be around 0.74. If it is slightly less, then poorly packed aggregate, then it will be around 0.58. For a single sized sphere, it lies somewhere around 0.58 to 0.74, and that 0.62 what we have discussed in the angularity number in the last lecture, that 0.62 came based on this packing density. That is, when a single sized spheres are being packed, that packing density was found to be around 0.62. So it lies somewhere between this 0.58 and 0.74, and this is how we got that 62% when we defined the angularity number. So in order to improve the packing density, instead of using single sized aggregates, we can go for multi-sized mixture of aggregates, so that the packing of aggregates gets compacted, and also our main aim is to reduce the void ratio, that is the porosity in between the aggregates. That will be reduced when we go for a multinary mixtures. Our packing density increases when we are using different size of aggregates, that is, the size of aggregates based on the proportions how we are using it in our concrete. So based on the size and its proportion, our packing density gets modified. And let's see an example of how the packing density and void ratio gets modified. Consider two aggregates A and B. A is finer and B is coarser. In figure 1, the aggregate, that is the fine aggregate named A, is being packed in a manner, standard manner, and in figure 2, a coarse aggregate named B is being added to the fine aggregate mixture. So, based on this, how the void volume gets reduced, let's see. In figure 1, we are having alone the fine aggregate arranged in a standard manner, and for that we are calculating the porosity, packing density, porosity, that is nothing but volume of solids to the total volume. We are calculating the porosity or the packing density, it is nothing but volume of solids to the total volume. Again, after adding the coarse aggregate to the fine aggregate mixture, again we are calculating the porosity, that is nothing but volume of solids to the total volume. Now, what happened in this case is the total volume has increased due to the addition of coarse aggregates, but it does not alter the voids which is already present in the fine aggregate system, but due to the increase in the total volume, the void ratio gets decreased. This is one example of how void ratio is being reduced. Now, let us see another example. In figure 1, they have shown us a coarse aggregate packing system, that is the coarse aggregate is being filled in a standard manner, and in figure 2, now we are introducing fine aggregates, that is the particle A, into the coarse aggregate system. Here what it happens is the total volume remains the same in both the cases, that is the volume is not altered due to the introduction of fine aggregate into the coarse aggregate system, but due to the introduction of fine aggregate, the interstitial spaces between the coarse aggregate is being filled by the fine aggregates and the void volume is reduced. In first case, because of the increase in the volume, total volume, the void ratio gets decreased, and in the second case, because of the filling up of the interstitial spaces between the coarse aggregates, the void volume gets decreased. Based on this, we can achieve the optimum fraction, that is the limit when the void ratio will be reduced, that is by increasing either the coarse content or by introducing the fine aggregate into the coarse aggregate system. If we draw a graph, then we can find the optimum void content, and from that void content, based on that we can design a mix having a higher packing density. Since we are introducing either coarse aggregate to a fine aggregate system or a fine aggregate into a coarse aggregate system, there comes an interference between the particles, and that we are going to discuss now. Particle interference. Let us have a look at the figure. The first one, in the first figure, it shows that the dark color is a coarse aggregate system and the fine aggregate are being packed to it, and because of that packing there arises an effect called as wall effect. That is, since they are not compactly packed, that leads to wall effect, that is called wall effect. That is when a coarse aggregate is being introduced into a fine aggregate system, then there comes a effect, there rises an effect termed as wall effect. In the second figure, a fine aggregate system is being introduced into a coarse aggregate system and there rises an improper packing, and that is called as loosening effect. This all happens because of particle interference. That is, a proper packing is not maintained between different types of aggregates. Different types of aggregates means a coarse aggregate and a fine aggregate system. If a proper packing is not ensured, then it leads to the development of voids. So, in order to ensure that whether the aggregate is properly packed or not, we are using the term grading of aggregates. So, as we seen already that the interstitial voids between the aggregates will be filled up by the cement paste. To ensure dispersion of these aggregates, we have to introduce amount of paste a little more than the, we have to introduce the amount of paste little more than the voids which is being present in the system. In order to have a good proper packing of aggregates, the code ensures the use of grading curves. Based on the grading curves, we can find out that what should be the size of aggregate and in what proportion it should be added to the mix to ensure a proper packing arrangement. Increasing the nominal maximum size of aggregate, that is, for in an already present system, in an already present aggregate, again we are introducing another nominal size of aggregate, that is, we are increasing the size of aggregate. By doing so, we can ensure better packing of aggregates. By doing so, the overall voids will get reduced and also the paste to be occupied between the aggregate spaces get reduced. That is, by increasing the mean nominal maximum size of aggregates, we are ensuring that the voids are getting reduced. For this, our codes have specified for fine aggregate grading. In our codes, they have ensured for fine aggregate grading 4 zones are available, that is zone 1 to zone 4. Zone 1 is coarser and zone 4 is finer. Based on the code's prescription, we can ensure that whether the packing density of aggregate is to a higher level or to a lower level. That is, by introducing the size of aggregate and the proportion of aggregate in the prescribed manner, we will be getting a good packing density. Nowadays, this is being done using the codes, but in the olden days, when these charts and grading curves are not available, they have done the proportions based on their experience. Let's have a look at the table. Here they have given the sieve designation 80, 40, 20, 4.75, 0.6 and 0.15, and the percentage passing, that is when we are having a 40 mm mean size and percentage passing 40 mm nominal maximum size of aggregate and 20 mm nominal maximum size of aggregate. When this 40 mm nominal size of aggregate is passed through 80 mm sieve, 100% should be passed. If it is going to be passed through 40 mm sieve, 95 to 100 should be passed, and 20, 45 to 75, and for 4.75 it is around 25 to 45, and likewise for 20 mm MSA. this has been arrived, and this table is being formed based on the experience which we had earlier. And the grading of aggregates can be done for multinary mixtures, that is not for a binary mixtures, that is either two sized aggregates only should be used, not like that. It can be extended even up to 3 or 4 sized aggregates. In the early periods, when these grading curves concept was not introduced, people made use of these mixed proportions based on the size and their experience. For better results and to have less particle interference, the amount of paste which is going into the system should be slightly more than the void content present in the system. This ensures better dispersion of aggregates. Next, we are going to discuss about fineness modulus. Fineness modulus is another way of defining the size of aggregates. Before this, to find the size of aggregates, we have passed the aggregate through a series of sieves, and based on the percentage of aggregate being retained or passed through a particular sieve, we were able to differentiate the size of aggregates. But this fineness modulus will tell you the size of the aggregate in a single number. Since the aggregate size cannot be expressed in terms of arithmetic mean, that is, since we are passing the aggregate through a series of sieves, we cannot tell that the size of the aggregate simply by taking mean of all the sieves. But this FM, that is fineness modulus, actually represents the size of the aggregate through weighted average. Represents weighted average sieve number, and this fineness modulus will tell you a single number, and that number does not directly represents the size of the aggregate, but it refers to the sieve number, and based on that sieve number we can classify whether the aggregate. This fineness modulus represents the sieve number, that is the number which the fineness modulus represents belongs to the sieve number, and it does not represent the size of the particle. The number represented by fineness modulus, that is fineness modulus equal to 2.13, 1.73, that the numerical value represents the sieve size and not the size of the aggregate. This weighted average is obtained as the proportion of the sieves, since the sieve sizes are not same. That is, in a series of sieves, the percentage retained in each sieve is taken, that is, the cumulative percentage retained in each sieve is taken, and that divided by 100 will give you this fineness modulus. And for representing this fineness modulus, we have to name the sieve sizes starting from 150 micron and above. This fineness modulus, that is by taking the cumulative percentage retained in each sieve and dividing it by 100, we will be obtaining this fineness modulus, and that fineness modulus number represents the sieve size. So before doing this, we have to number the sieves starting from 75 micron. For 75 micron fineness modulus FM equal to 0, 150 micron FM equal to 1, and it goes on like this. The next sieve size is represented by the number 2, 3, 4, and it proceeds. So, the number which the fineness modulus represents doesn't mean the size of the aggregates, but it represents the size of the sieve. Next we are going to see about surface modulus. In the surface modulus, the specific surface area of the aggregate is taken into consideration. Why we are seeing this surface modulus is some codes is based on the surface modulus and some codes will be based on fineness modulus. This surface modulus has an impact on workability. This surface modulus is related to specific surface of the aggregate, and some codes will rely on surface modulus and some codes will rely on fineness modulus. As the sieve size increase, the surface modulus will decrease. That is, for aggregate of higher order, higher sizes, the surface area gets reduced, and for aggregate of smaller sizes, the surface area gets increased. Since this surface area will play a major role in workability and the percentage of water content, this surface modulus is being studied. That is, when the surface area of the aggregates get smaller, the more water content will be required, and if the surface modulus is getting increased, then it means that a lesser water content will be required. So, each definition has its role when designing a concrete mix, and that's the reason why we are learning all these terms in advance before we are going to design a concrete mix. While aggregate grading is done, we have to ensure that whether the sizes and proportions of different aggregates are being done in a proper manner. If it not so, then it leads to either a pore graded or a gap graded system as shown in the figure. The first one represents the well graded system, that is, the different sizes of aggregates and proper proportion between them has been ensured in that system. Next represents a poorly graded system, that is, there they have used only a single sized aggregates, and in the gap graded system proper size proportioning has been not done between the aggregates which are being used in the system. To ensure better packing density, we have to see whether it is a well graded, gap graded or a poor graded system. Combining aggregates or aggregate blending. When we can go for this aggregate blending is based on the grading curves. When we are not obtaining the specified percentage of passing through a particular sieve, then we can go for this aggregate blending. When two aggregates are not being desirable to the grading curves which is being prescribed already, then we can go for this aggregate blending. That is, the aggregates from two different sources can be blended in such a way to get the desired grading curves. And this is all related to the aggregate terms which plays a main role when it is being used in concrete design. Now we are going to discuss about the properties of aggregates. The first property is related to hardness and toughness, that is the strength of aggregate. Since the aggregate is being obtained from the parent rock, and as we saw already that certain factors will be based on the parent rock characteristics and certain properties will be based on the individual aggregates. Likewise, the strength property will be based on the parent rock property. So, to determine the strength of the aggregate which we are going to use in a concrete, different tests are being done to determine the strength of aggregate, like aggregate crushing strength, impact test, abrasion test. Based on these tests, they have prescribed a certain value, range of values, and if our aggregate falls within the range of values, then we can tell that our aggregate is of a good quality aggregate, that it possesses the strength aspect as it's of a parent, that is it possesses the strength aspect, that is it possesses the strength aspect as that of the parent rock. In aggregate crushing strength, the aggregates passing through 12.5 mm sieve and retained on 10 mm sieve will be taken in a specified quantity, and it will be placed in a standard manner and load will be applied to it. After applying the load, we will take the aggregates and sieve it on a 2.36 mm sieve, and the percentage of passing to the total material taken will give the aggregate crushing value. Likewise, for abrasion test, we will be choosing one sieve size of the aggregate, and steel balls will be introduced in a rotating drum, and again there we will be taking the material and we will be sieving, and the percentage passing through the total material taken will give us the aggregate abrasion value. And likewise for impact test, based on this the strength of aggregates will be noted. Next is bulk density. This bulk density is nothing but the mass of aggregates required to fill the container having a unit volume. How much of aggregates goes into a particular volume, that will give us the bulk density. Why we have to do this bulk density test is to ensure whether a high cement content is required or a low cement content is required for that aggregate system when it is to be used in concrete. This bulk density test is mainly done to ensure whether there is a large pore space or a less pore space based upon the aggregate packing in a unit volume of container. Lower bulk density will provide us with more void spaces, whereas higher bulk density will provide us with less void spaces. Next, specific gravity. It is defined as a ratio between the weight of a given volume of aggregate to the total volume of aggregate. Specific gravity is defined as a ratio between the weight of an given volume of aggregate to the weight of an equal volume of water. So based on this specific gravity, we can ensure this specific gravity test will be later used when the specific gravity will be later used in a concrete mix design. So the specific gravity is nothing but the ratio between the weight of the volume of aggregates, that is it may be permeable or impermeable aggregate, to the weight of a volume of water. So the specific gravity range of rocks will be in the order of 2.6 to 2.8. Next, moisture content. This moisture content plays a major role when we are mixing. This moisture content plays a major role when designing a concrete mix. Generally, we will be having 4 kinds of aggregates. One is bone dry or oven dry, next is air dry, and third is saturated and surface dry condition, and fourth one is the moist condition. Among the 4, SSD, saturated surface dry condition, will be among the 4, saturated surface dry condition aggregate will be chosen for making the concrete. The reason is, in the saturated surface dry condition, the aggregate inside will be in the saturated surface dry condition aggregate, the aggregate will absorb the water and its surface will be dry, so that the water inside the aggregate will neither be available for mixing or it will take part in the hydration reaction. That is, it will not interrupt the hydration process, or it will not even take place in mixing. So that's why we prefer for this saturated surface dry condition aggregate. If it is not so, when we are using the remaining 3, that is air dry or air dry or oven dry or moist aggregate, they will either contribute during the mixing or hydration process, or they will absorb the water which we are providing for the hydration reaction. So we are using the saturated surface dry condition aggregate. The adsorption capacity of coarse aggregate will be in the range of 0.5 to 1%. The adsorption capacity of coarse aggregate will be in the range of 0.5 to 1% weight of aggregate, whereas for fine aggregate it will be around 10%. And another important property while discussing fine aggregate is bulking. Bulking of sand. The bulking of sand results when fine aggregate is subjected to moisture content. That is, when the fine aggregate absorbs moisture from the atmosphere, that results in bulk of volume, that tends to rise in the volume. Why the volume increase happens is due to the adsorption of moisture. Since the sand absorbs moisture, it forms a coating around it, and that leads to the separation of particles, sand particles, and this is the reason for bulk in volume, and this is the reason why the volume bulks due to the moisture absorption. This will create a serious issue if the batching is done based on volumetric batching, but if the same batching is to be done by weight batching, then its influence will not be much more. This increase in volume will take place up to a certain percentage of moisture content, and beyond that further increase in the moisture content will lead to the decrease in the volume content. So up to a certain limit, when we increase the moisture content, the percentage of bulking takes place to a higher limit, and after that even if we increase the moisture content, it leads to the reduction in the bulking, and that point is termed as the optimum moisture content. But anyway, it has a less role when we are using this sand in a weigh batching system, but if the batching is done based on volume, then it has a serious issues, since this bulking leads to harshness of sand. This bulking of sand when used in a volume batching leads to serious effects. Next, we are going to discuss about the cleanliness of the aggregates. The aggregates which is to be used for concrete should be free from impurities. The reason is, if suppose the finer material than sand, that is a silt and clay, is to be present in the aggregate, then it prevents if silt is present, then that increases the water content ratio, and if clay is present, it reduces the bonding of aggregates. So we have to ensure that our aggregates to be used in concrete is free from impurities. So to ensure this, what we are doing is, a sample of sand is taken, and for that sample, in that sample, to ensure this, a sample of sand is taken and 3% of sodium hydroxide is mixed with it, and it should be allowed for 24 hours, and if there is any color changes during the 24 hours, then it denotes that the sample is not free from impurities. So we have to ensure that our aggregates is free from any impurities. Next, soundness. Soundness of aggregate refers to the ability of the aggregate to withstand any volume expansion. This volume expansion will happen when our concrete is exposed to freezing and thawing condition, frost conditions. This volume changes will happen when our concrete is exposed to freezing and thawing, variation in temperature, alternate drying and wetting, etc. So our aggregate should be sound enough to resist all these volume changes. So aggregate should be sound enough to resist all these changes during freezing and thawing or alternate wetting and drying. Next, chemical properties. And already we have discussed it during the introduction to aggregates, that our aggregate must be inert, and I have told you the reason already why it should be inert. If suppose it is not inert, then it leads to durability related problems. Some aggregate contains reactive silica within them, and when such aggregates are being used in concrete, they will react with the alkalis present in the cement, and when the concrete hardens, this gel causes expansion of the concrete, causing cracking of the concrete. And next we are going to discuss about thermal properties. The thermal properties are mainly concerned about coefficient of expansion and thermal conductivity. That is, in the concrete we are using three different materials: aggregates, cement paste, sand, and each one will have its thermal coefficient ranges. If these ranges are within the adaptability limit, and if any incompatibility arises, then it leads to serious issues related to durability conditions. That is the coefficient of expansion of the coefficient of expansion of the particles, that is the aggregate, should be in line with that of the mortar, and it should be in line with that of the concrete. If it is not so, then it leads to serious durability issues. In aggregate, we have discussed about its shape, size, texture, and for defining the shape and size, we have introduced new terms such as angularity number, sphericity factor, and after that we have discussed how the aggregates have to be packed in order to ensure less voids, that is nothing but porosity, and how we can combine aggregates to reduce the voids. And after that we have discussed about the properties based on its strength, aspect, and chemical properties, etc. And next we have discussed about the properties of aggregates relating to strength, hardness, toughness, cleanliness, chemical properties, etc. Now we are going to discuss about water. Since the water is the main ingredient which ensures the hydration process, next we are going to discuss about water, and this water plays a major role for the hydration process. So we are going to discuss how the water properties should be, how it influences the strength of concrete. Likewise, while using this water in concrete, a threefold action is happening inside, that is, it ensures proper dispersion of particles, it produces CSH gel, and it enhances workability. So the water to be used in concrete should be free from impurities. A popular yardstick says that a potable water is fit for concreting purpose. Potable water is nothing but a drinking water, but all drinking water cannot specify to the standards of mixing water which is to be used in concrete. So there lies a certain range within which, and based on that the water can be used for concreting purpose. The main impurities in water are due to chlorides, sulfates, organic matter, wastewater, etc. If chlorides is present in the concreting water, then it leads to acceleration of hydration reaction or corrosion of steel. When chlorides containing water is used for concreting purpose, it accelerates the hydration process or leads to corrosion of steel. When sulfate rich water is used for concreting purpose, it leads to reformation of ettringite. Then the organic matter rich water should not be used for concreting purpose, and again the wastewater also should not be used for concreting purpose without any recycling process. So this water to be used for concreting should be free from all the above said factors like chloride, sulfates, etc., organic matter, sugar, wastewater, etc. And another important factor is that the water to be used in concrete, and another important factor is that the water to be used to concrete is controlled by a factor termed as water-cement ratio. This water-cement ratio is given by Abraham's law. The quantity of water to be used in concrete is governed by a parameter called water-cement ratio, and that water cement ratio, how it affects the strength of concrete is being referred by Abraham's law, and the Abraham's law states that S equal to 748 plus 7 power x, where x equal to water cement ratio and S equal to compressive strength of concrete. So, the compressive strength of concrete varies non-linearly with the water cement ratio. The strength of concrete varies non-linearly with the water cement ratio, and that is termed as Abraham's law. So, the quantity of water to be used in concrete for mixing purpose should be within the certain limit, and that is termed as water cement ratio, that is the weight of water to the weight of cement. Instead of volume, here we are using the weight of water to the weight of cement.